Hello everyone, this is Solomon. This is a mechanism sessional project on which we will discuss on the design, simulation and analysis of a windshield wiper mechanism. Our team members are SASHANK RYALI, DEEPAK Polishetty and ASISH PILLI. Our objective is to synthesize and simulate the windscreen wiper mechanism. Without quick return, we visualize the wiped area and innovations like adjustable wiping range, estimate speed, and acceleration for a constant speed motor and approximate motor torque while neglecting dynamic effects. The Grashof analysis ensures our wiper mechanism achieves the motion we need, a full rotation of the crank with an oscillating rocker. First we calculated the lengths for each link: crank O2A 30 mm, coupler AB 200 mm, rocker BO4 80 mm, ground link O2O4 158.11 mm. Using the Grashof condition, we sum the shortest and the longest links 30 mm plus 200 mm and compare to that the sum of remaining two 80 mm plus 158.11 mm. Since the sum of the shortest plus longest is less than the remaining two, the Grashof criteria is satisfied. This means the mechanism is a Grashof crank rocker type. The crank can complete a full rotation ideal for continuous motor-driven wiper action. The rocker oscillates, moving the blade back and forth. The coupler produces complex motion which drives the wiper link CD, ensuring thorough coverage of the windshield. Using this selected link length, we model the exact 4-bar plus wiper arm mechanism ensuring correct pivot spacing. The mechanism consists of a crank, coupler, rocker, and the extended wiper arm. We included windshield height and blade geometry to match the problem sketch. Ground link positioning follows the required horizontal and vertical offsets. The full assembly is prepared with revolute joints, ready for motion simulation. We analytically derived theta4 using vector loop closure equations, giving the standard form A cos theta4 plus B sin theta4 is equals to C. Using half-angle methods, we solved for the rocker angle exactly. This converts the input crank angle theta2 to the output rocker angle theta4 in closed form. Eliminating trial and error, graphing, and removing the quick return effect, a solution was validated with SolidWorks motion and used to compute the tip velocity, acceleration, and swept area. A SolidWorks motion study models the mechanism with the same geometric constraints as a vector loop analysis. The crank rotates, driving the coupler and rocker to generate oscillatory wiper arm motion. Simulation results closely match the analytical equations for rocker angle. The purpose of simulation is to validate our analytical rocker angle, visualize the actual wiping motion, extract velocity and acceleration profiles, verify the absence of quick return effect and generate the wiped area envelope. We trace the tip position of the wiper for various crack angles. Extreme positions were plotted to show the outer and inner boundaries, and the region between is marked and hatched. This graphical method closely resembles typical automotive wiper behavior. The swept envelope between extreme rocker positions defines the effective wiped area. This slide focuses on how quickly the tip of the wiper blade moves while the motor itself spins at a constant speed. The velocity of the wiper tip changes non-linearly. Peak velocity of 0.58 meter per second minus 1 in the central sweep region. Velocity minima at the ends of each sweep. Velocity reaches zero each exactly when the blade reverses direction. This variation in speed is typical in crank rocker mechanism caused by the geometry of the linkage. Practical interpretation are: the higher speed in the middle sweeps away water efficiently. Lower speed at the ends prevents loud slapping noises, reduces wear, and prevents overshoot. In the wiper tip acceleration analysis, we analyze how fast the tip of the wiper accelerates as it sweeps across the windshield from the plot. The key observations are: acceleration isn't uniform, it fluctuates as the wiper moves. The acceleration peaks at around 3.8 meter per second square and drops to zero near reversal points where velocity reverses direction. Sudden spikes in acceleration occur when the linkage aligns in certain ways. These repeat every half cycle and confirm oscillatory motion. Practical engineering impact is: high acceleration peak demands greater motor torque, especially when the wiper quickly changes the direction. If the spikes aren't managed, they can cause blade juddering or unwanted noise. Real car wipers uses elastic hinges and compliant materials like rubber to absorb the shocks and protect components of the wiper blade, primarily due to friction between the blade and the windshield. Purpose and approach: our aim is to evaluate whether the chosen mechanism and motor are suitable for an automotive wiper application. We focus on static analysis, considering only constant, non-accelerating loads, which simplifies calculations and give a conservative estimate. Key assumptions are: only static resistive forces are included, namely friction and contact force between blade and glass. We treat the wiper blade as a slender member subjected to a distributed load across its length. The reaction force between the blade and windshield is assumed constant during each sweep. The perpendicular distance from the blade's pivot to the line of action of this resistive force influences the required torque at every instant. The torque required tau at any point is given by tau is equals to F resistive into R. Maximum torque is needed when the distance is largest, typically when the blade is stretched farthest from the pivot and angle is greatest. Minimum torque occurs when the blade is closest to vertical, reducing the lever arm. The engineering insights are: the torque profile closely follows the blade's path, highest at sweep extremes and lowest at the midpoint. The analysis confirms the need for a safety margin in motor selection, especially to account for conditions like rain, dirt, or an older, less flexible wiper blade. Thank you for watching our presentation and exploring the engineering behind a windshield wiper mechanism design.